Today we'll talk about thermal concepts, primarily temperature, internal energy, and heat. I'm going to introduce a simple model of a solid. It's not particularly realistic, but it will help to explain how we might go from a solid to a liquid to a gas. So it gives us kind of a visual representation, so it has some use to us. So here's a molecule in a solid, and there's another molecule in the solid. And of course, there'd be all kinds of molecules in that solid, and they'd be in a big lattice here. It'd be three-dimensional, so we'd have lots of molecules in behind as well. I'm just going to focus in on two molecules, this one and this one here. Of course, there are forces between the molecules causing them to attract and repel. And I'm going to represent that by springs here. So I'm going to have a spring coming across each molecule so that those molecules are attached in the solid. I'm going to do something kind of unusual. I'm going to draw a rod right here. And so there's my rod coming down. In the middle of that rod, I'm going to make a little cylinder. And at least in the liquid case, this cylinder is going to be able to slide up and down. In the solid case, the cylinder is going to be fixed on there, maybe with a bit of glue. So typically, what's happening in a solid, we would have these molecules able to vibrate back and forth in their lattice positions. And in the solid case, this slider is fixed. So there's a bit of glue holding that slider in place. Now, if we throw some heat into our system, of course, the molecules begin to vibrate more, and the glue comes loose, and that slider begins to slide up and down. And that gives another degree of freedom to the movements that the molecules can make, and that gives liquid its unique properties. So this becomes a liquid when the slider can move on the rod. Okay. Like I said, it's not a particularly realistic model, but it gets at the idea that if we throw some heat in, these molecules can vibrate enough to change the amount of motion that's available to the molecules. And then, of course, in the gas case, we would have the situation that the rod disappears and the springs break loose so that the molecules would become free. There might be, in the gases we'll study, ideal gases, there would be no electrostatic interaction whatsoever. In real life, there might be some interaction there, but it wouldn't be like a spring. So in a gas, the rods and springs disappear. So we can kind of get a picture of going from a solid to a liquid to a gas. In the big picture, there's just two forms of energy there. We've got the molecules. They've got energy because of their motion, primarily vibration, at least in a solid. And so that would be their kinetic energy. And of course, there's energy stored within the bonds or those springs in our model, and that would be a form of potential energy. And so, like I said, all forms of energy ultimately come back to being either kinetic or potential in nature. And so we can talk about the internal energy in a solid or a liquid or a gas as being composed of the kinetic energy of the molecules and the potential energy of the molecules. So what we call heat and what the IB prefers to call thermal energy is energy in transit from the internal energy of one body to the internal energy of another. So in mechanics, when we were talking about transfer, we talked about work. That work was the cause of any energy transformations. Now in thermal physics, we talk about heat or thermal energy when we talk about the transfer of energy from the internal energy of one body to the internal energy of another. Temperature is what tells us what direction that heat will flow. If I put my warm hand on the cold desk, I know that the desk will get warmer and my hand will get colder because the heat flows from my warm hand to the cold desk. And it would never be the opposite case where my hand got warmer and the desk got colder. Heat always transfers from a higher temperature to a lower temperature. And we say that when two objects are in the thermal equilibrium, that is when they're at the same temperature, then no heat will flow. No thermal energy will flow. And this is called thermal equilibrium. We sometimes say that a thermometer reads its own temperature. So if I take a thermometer and I put it into this bath, we'll say the bath's at maybe 80 degrees, thermometer would be at room temperature, then heat's going to flow into the thermometer until the thermometer reaches thermal equilibrium with the water. And of course the liquid will rise and we'll be able to read the temperature. Now that's no problem, but it becomes a problem. Let's say if we make our sample of water much, much smaller. And now we put our thermometer in. Now we've got a little bit of a problem because the thermometer is going to absorb some energy. And when it does that, it's going to change the temperature that it's trying to measure. And that will mean that it won't read the proper temperature because we're disturbing the temperature itself. In summary, heat always flows from a high temperature to a low temperature. The internal energy is going to decrease on the high temperature side, and the molecules are going to slow down and they're going to get closer together. On the low temperature side, the internal energy, of course, it increases. The molecules move faster and get farther apart. Now, some of you might be asking about, well, won't we have more bonding energy if the molecules are closer together? Right? Isn't there more energy stored when the molecules are closer together? And so let's take on that question right now. So bonding energy, it's the electrical potential energy stored between molecules due to the positive and negative charges that attract each other. Right? So there's an attractive force pulling those charges together. And that energy is going to be negative because those two objects are trapped by one another. In other words, if I wanted to set those two molecules free, I'm going to have to apply some forces. I'm going to have to do some work, and I'm going to have to do some work to separate those charges so that they're free of each other. And when they're free of each other and they're not interacting, that should be zero potential energy, zero bonding energy. So if we get molecules farther apart, then we have to do work, and we're going to make the potential energy less negative. We are increasing the potential energy, but we're making it less negative. Free particles should have zero bonding energy, and we're going to have to do work to get them free. Little cartoon I like to use to help you remember that. We've got a fighting couple here, and the one says to the other, it's less negative when we're farther apart. So when molecules separate, the bonding energy becomes less negative and is therefore increasing. If we want to think on the molecular level, the total internal energy of a body has to equal the sum over all molecules. It would be the sum over all molecules of their motional energy and their bonding energies. And temperature, you've probably heard this before, the temperature of a body is a measure of the average kinetic energy per molecule. So we can't even describe temperature if we only have one molecule. Even though it would have an average kinetic energy, temperature is really a statistical quantity, and you need to have millions of molecules, some of them moving slow, some of them moving fast, and then we'd work out the average kinetic energy per molecule. And that would be a measure of temperature. Okay, and one last activity. We've got heat flowing into a cube of ice, causing it to melt and then boil. I want you to comment on the changes in how the internal energy is stored as the heat is absorbed and the water changes from solid to liquid to gas. So maybe take a little time now to think about that, and then I'll flash the solution on the screen, or at least my solution. Okay. So it's the solid form, the negative bonding energies are are dominating the kinetic energies, and those sliders would be fixed. As you move to a liquid, the kinetic energy of the molecules overcomes that solid bonding energy, and the sliders begin to slide around. You're still going to have an overall negative energy because bonding energy is bigger than kinetic energy. And then eventually when you get to a gas, the kinetic energy breaks everything loose, and the molecules end up being free. And by and large, the only type of energy that the molecules have will be kinetic energy, and there'll be no, at least in an ideal gas, no interaction between the molecules at all.